Hey everybody, welcome to .NET Conf Day 3. Again, this is what we're calling Beginner Day. We are in the .NET Fundamentals track. And with me I have Bob Tabor, who's going to teach us about async and await in C#. How's it going, Bob?
Hey, it's going good, Javier. How are you?
I'm doing great. So go ahead, let's get started with it.
All right. So I'm going to turn off my camera. Howdy, everyone. Hello from Dallas, Texas. And now I'm going to turn off the video, and we're going to start the slides. Javier, does this look about
It
right?
looks perfect.
Awesome. Here we go. So first of all, hey, thanks a lot for attending. I know we're expecting like millions of people to watch this live, and I'm up against Pardon the Interruption on ESPN, and I hope to beat them out in the ratings. So thanks for coming to this session. Just to get started, I want to make sure to set the expectations right up front that this talk is really aimed at a post-beginner audience. So to clarify, I'm going to assume that you've been following the track of content at the .NET Comp, helping to learn how to build applications on the .NET platform, right? So if you are an experienced C# or .NET developer, then frankly, I got some bad news for you. This talk might be a little disappointing because I'm going to be covering this topic matter for those who are absolutely new to the topic. So I hate to chase people away, but you might be better served looking at some of the more advanced resources to gain a deeper knowledge. Now, unfortunately, I have that slide at the very end, so you're kind of on your own unless you want to come back to the very end of this talk. But as you get started with one of the frameworks, whether you're going to set out to build desktop applications or web-based applications with ASP.NET, MVC or MVC Core, or you're going to build cloud applications, no matter what you want to build on the Microsoft platform, undoubtedly you are going to encounter methods in that framework that have the suffix async on the end. So whatever it is, async, right? And if you look at the code examples that demonstrate how to use that given framework, you're going to see a few C# keywords like async, task, await. And so if that's kind of new to you, then you're in the right spot. This is exactly where you need to be right now. So generally speaking, you could just follow the examples for those frameworks and the methods that have the little async at the end. Just looking at, there's a pattern that you can follow, and we'll take a look at that pattern here in just a moment. So that anytime you see that async method in the name of the method, you can get pretty far just by following this little pattern. And the pattern is basically like this. And let me pop out to code real quick and show a quick code example. Here we are in Visual Studio. I've got a real simple async console application. I hope you can see my desktop. And this really doesn't do anything, but you're going to see this type of these 4 lines of code used often throughout this talk. So essentially here we're just going to go out to my website, devu.com, and we're going to say, hey, grab the entire HTML from that home page, and then I want to display it out in a console window. And so I made this little method called doIt async. And you can see, first of all, I followed a convention whenever I created this method to use the term async at the end. Here I'm calling a method on the HTTP client, the object that actually will go out and make the call out on through all the network protocols, through my machine out over the internet and so on. It has async in the name of the method, and then here, once we get the result back, I'm reading that result as a string, ultimately to get the content. So that's the first kind of part of the pattern. There's another part of the pattern where you see this await keyword that's used right before the method. This is actually an operator called await. We'll talk about what it does later, but I don't even really have to know exactly how this works. If I follow that pattern, it just works and it gives me performant code, or at least it helps me to avoid some sticky situations that we're going to talk about just here in a few moments. And then the last kind of part of the pattern that you'll see is this async keyword here in the method signature, and we'll talk about what that means. And then finally, you'll typically see either the word task or a generic version of the word task or the object task, and in this case, it's a task of type string. So that's the pattern, and if you follow the pattern, you can usually get the results that you need to get. But let's switch back over here to my slides. And that's really the great thing about the C# async features, is that you really have to try to not do it correctly. If you forget one of those operators or keywords, you'll see a red squiggly line. If you use some of the features of IntelliSense, it's going to try to help you get the statement right. But what we really want to do in this session, however, is dive deeper than that. And we want to understand what problem async and await is actually trying to solve. Once we can build this conceptual model in our mind, then we can come to a better understanding of what's going on and how is it actually doing it. And then maybe, just maybe, at some point in our programming careers, we can move past simply following the pattern, simply tolerating those extra keywords that we have to use, and actually harness that in our applications. So let's start off by talking about the problem of long-running operations. And I'm sorry, I kind of changed the direction of this whole talk a little bit earlier, and I don't have lots of pretty graphics and things of that nature. I actually spent all my custom graphic budget on Starbucks so that I could stay awake through the night and work on this. So I apologize, it's going to be thick with text, but hopefully we'll get through here in just a moment, then we can get on to some code examples. So the problem of long-running operations. So many software applications that you'll build will require long-running operations. In other words, some computing task that takes a relatively long amount of time. And the term relative is important here because we're talking about something that's long-running from a computer's perspective, which could be anything longer than just a few milliseconds. So if we're not careful, long-running operations could wholly consume the computing resources that have been devoted to running our application and block any further operations for the application being performed. So when your application is started, the operating system will devote a portion of the CPU to executing your application. It's a very complex process. I'm going to be oversimplifying just about everything here just so that we can build at least the beginnings of a mental model, and then you can build onto that over time. But at any rate, yeah, so we can get in over our heads pretty quickly on this sort of stuff. Let's just speak in broad generalities. When your application is started, the operating system will devote a portion of the CPU to executing your application. And that portion of the CPU is typically called a thread. And there are many layers of software between your C# application and the computer's hardware, the CPU. There's the operating system, the windowing subsystems, there's the .NET Framework runtime. Again, speaking here in broad generalities, but ultimately a CPU thread is executing your code. So while the CPU thread is executing your code, it's only working on one thing at a time. And you can see that whenever you set a breakpoint and you start to step through each line of code in your application. But generally speaking, even though it's only doing one thing at a time with your application, that's okay because most operations happen so quickly that it's hardly an issue. You don't even notice. It happens in microseconds, not milliseconds. But once the CPU thread of execution encounters something that takes a long time, that something that is taking a long time is usually called a blocking operation. So blocking simply means that the CPU thread of execution is tied up, and so it can't perform other tasks. And we'll talk about how blocking operations impact performance on desktop or device-based applications versus server-based applications like those that are handled by a web server. We'll talk about that in just a moment. So there are two basic types of blocking operations that happen. You can see at the bottom of the slide there are CPU-bound blocking operations, and then there are I/O-bound blocking operations. So what's the difference between the two? A CPU-bound operation is something that is compute intensive. In other words, there's a very intense amount of actual computation going on. And this could be anything from a difficult mathematical algorithm that requires the calculation of large numbers, or the creation and the management of variables or objects in the computer's memory. You might have it filled with enormous amounts of data that need to be processed and calculated in some way, or ultimately updating what is actually seen on screen. In most cases, if you're writing business applications, that's the type of applications I would say that I write. You probably are not going to experience many situations where you have a CPU blocking operation. But if you plan on writing games, or if you're going to be building scientific applications that are very mathematically intensive, then you might in fact encounter CPU-bound blocking operations. I want to talk in more depth about the second one, the I/O bound operation. So an I/O bound blocking operation is something that requires the CPU to wait on some external resource like hard drive access, which is super slow whenever you compare it to how quickly the CPU can actually function. A good example of an I/O bound operation is also network access. So like retrieving data from the server on either the same network or even worse, retrieving data from some server out on the internet across the world. So that acronym I/O, it actually stands for in, out, and in this context, it's referring to something that is external, outside of the boundary of what the CPU can be responsible for handling. So something that the CPU has no direct control over. It's usually much slower than what we said CPU bound operations, because you're waiting on something that could potentially take milliseconds or even full seconds in order to return a result. So again, I'm not really aiming for absolute accuracy as I describe this. I'm just trying to provide a very high level, low detail explanation. So whenever your instructions in your code that you write rely on some external resource like the hard drive or network resource, internet resource, whatever the case might be, the CPU, what is it doing? It's just sitting there and it's waiting for the result of that operation. Now, in most cases, this means that it's waiting for a particular region of memory to be filled up with data, and then it can access that data through what's called a stream. So if you're attempting to read the contents of a file, the .NET Framework will work with your operating system's low-level APIs to interact with the data on the hard drive and load it into memory. And then once that stream starts flowing with data from the external operation, then the CPU can begin processing that data in that stream and continue on with the instructions of your application. But while it's waiting for that file to be loaded, it's sitting there blocking, doing absolutely nothing. It could be doing something more interesting for your application or giving the end user some responsive feedback as to what's actually going on with the application under the hood. But so in a nutshell, that's what you need to know as a baseline knowledge about how the computer runs your application and how it allocates memory to your application, how it interacts with the world around it, whether that be hard drives or network resources or even streams. So this distinction between, going back to the previous slide here, at the very bottom, CPU bound and IO bound blocking operations is really critical to understanding the problem of how your code blocks the CPU thread of execution that's running your application. Also, this distinction is important because it impacts how you actually go about solving that issue in C#. So let's move on here. Okay. So the impact of I/O bound and CPU bound operations really depends on the type of application that you're building. So if you're building, for example, we'll contrast building client applications, which are either desktop applications that run like on your laptop or on your desktop computer, or device applications. So this would be something like a phone, for example, or on a tablet. I'm just going to group those together and call them under a general umbrella term of client application. So if you're writing one of those styles of application as opposed to a server application, which we'll come to in just a moment, then the impact of a blocking operation is that the application becomes unresponsive to the user. So I'm sure that at some point, as you've used some sort of application on your phone or on your Windows desktop, that the application seems to lock up on you. It just doesn't respond to repeated clicks if you're using a mouse, or it doesn't respond to gestures on the user interface elements. So you're trying to scroll on a web page or on some game that you're playing, and it stutters. It doesn't respond immediately to whatever you're trying to do. Well, the problem there is that the same thread of execution that was responsible for updating the user interface is probably blocked. So it's sitting there waiting for some information from an external resource, whether that's local storage or out on the network somewhere. So once the CPU's finished that blocking operation, then it can refresh the user interface. But at this point, we're concerned with user experience. You see the letters UX on the slide there. That means user experience. what the user is experiencing while they're using your application. Is it a friendly experience, or is it a very frustrating experience? So I've read that a human can detect even a few milliseconds of unresponsiveness, and a human can become annoyed or even concerned about the stability of the application's performance after just a half of a second of a stutter or a pause, half a second of unresponsiveness. And from my own personal experience, I know for a fact that a human can become irate after just a few seconds of unresponsiveness. So that's clearly a problem that we want to solve for our end users. There's been a lot of frustration on the part of users, myself included, whenever I'm browsing a website or using an app and I attempt to scroll and it feels like the device is hanging up or it's stuttering, or even for a tiny amount of time, it's just not responding to whatever I want to do. I can't explain it. It's just not a satisfying experience. Do I still get to the information I want? Yeah, ultimately, but it's just not right. So there are actually ways to mitigate this, like the use of progress bars or spinners that you see on a lot of websites. And what that attempts to do is kind of become a surrogate for the real solution to the problem. It attempts to explain to the user that the application is still working, but even seeing a spinner pop up or a progress bar, for me personally, that's not entirely satisfying, especially whenever you're trying to scroll or interact. You don't want to see a spinner pop up. So as Microsoft years and years ago started to venture into the brave new world of creating operating systems for phones and tablets, which are typically equipped with less capable CPUs in order to save battery life and stay cooler inside of the casing, Microsoft became obsessed with the notion of a fast and fluid experience for the end user. And that meant that they needed to provide developers with the tools to easily create applications that could overcome some of these blocking scenarios. So that's why we got the async features of C# and the async methods and the user interface frameworks around that time, around 2012. So that's how blocking operations impact the client or client applications. But blocking operations can also have a dramatic impact on server-style applications. So if you're creating, for example, an ASP.NET application, a network request comes in over a given server port. Ultimately, that request is routed to a server. And let's talk in terms of web servers, but this could be true of really any kind of server. Like if you have SQL Server out on in Azure, for example. Anytime you have some style of server application, that request is going to be routed through the correct port for the given type of data that's being passed through it. So the server receives the network request. It looks at the applications that have been installed on the server that have been mapped to handle requests on that specific IP address. And that application is then loaded and executed in the context of the web server. So in other words, a web server typically keeps a pool of CPU threads hot and ready to go. And then they can be allocated towards this new request that just came in. So a thread is assigned, the application is loaded into the thread, or the thread actually begins executing the instructions in the code that you wrote, and the CPU begins to operate through the code logic. So here again, a long-running CPU-bound and I/O-bound operation will affect performance, but in a slightly different way than what we talked about with client-type applications. In these cases, in a server-style application, the application is running, but the user probably accepts and tolerates the fact that the website is slower than, say, a native client application. So the real issue is not the client, at least not at first, but rather on the server itself. So the longer it takes for a CPU thread of execution to complete its task and return to the pool of available threads, the less available those threads are for handling other requests that are coming in. So requests potentially can start piling up, or they begin to queue. Maybe the web server starts to cache them to disk, but the web server will do anything in its power to keep the pace, even if it has to do the caching little dance with the incoming requests. And hopefully, at some point, it can catch up as all the traffic requests begin to die off. But of course, the worst case scenario is that the server just can't keep up with all the requests that are queued up, and it has to ignore new incoming requests. So at that point, the user's software, like your web browser, for example, it has to make a decision. Should it continue waiting for that operation to complete? It's not getting any response back from that server on the other side of the world. Or should it notify the user that it just couldn't access that resource, is not available right now, and maybe you can try again later? So ideally, the client software would have some retry logic in it where it actually tries a second time. Maybe packets were lost in transmission or whatever the case might be. But ultimately, the client, in this case maybe the web browser, it may decide that it's time to give up and tell the user that it's just not going to happen now, and that maybe they should try again later. But back on the server, because that's really our focus here, blocking code means that the company might need to spend some more money on better servers or more servers, often referred to as either scaling up or scaling out. So those are the basic problems that we're trying to solve in this session, and it all stems back to code that's blocking the thread. So these long-running thread blocking operations are usually unavoidable, but there are some options that, as software developers, that we can take to actually mitigate them. And one option is to build a multi-threaded application. So in other words, what if our application could employ more than one thread to do all of this work, like especially in a CPU-bound scenario? That would especially be ideal whenever you could use one thread to update the user interface and another thread to actually perform that calculation, or use 2 or 3 threads to actually perform the calculation behind the scenes and then update or synchronize somehow back with the user interface to kind of to give the end user some notification that things are actually happening and we're not just standing still in the water. So building a multi-threaded application is always an option, and the .NET Framework has allowed developers to do that from the very first version of the .NET Framework back in 2002. However, historically, it's been challenging to get that right. First of all, it's difficult to debug a multi-threaded application. And secondly, it's difficult to synchronize the state of data across the threads. And then you also have to deal with conflicts whenever you have 2 threads that want to access the same memory region to get at the same data, which is typically known as a contention. So creating a multi-threaded application isn't impossible, it's just challenging. And because it's challenging, many developers just avoided it if at all possible. And furthermore, building a multi-threaded application primarily solves one of the scenarios that we talked about. Again, it's really more in line with CPU-bound blocking operations, but what about the other scenario? And that's probably the scenario that you and I, if we're building websites and business-style applications, that we're going to encounter, the I/O-bound blocking scenario. Again, in that case, the issue really isn't the workload, but it's actually the opposite. It's the lack of work. Your thread is sitting there doing nothing, and it could be responding to the user. So that's kind of the option number 2 here. In these situations, you might want to employ an asynchronous programming model based on the notion of promises and futures. And so there's 10 years between the point in time when the .NET Framework 1.0 was released, C# 1.0, and then 10 years later in 2012 when the .NET Framework 4.5 was officially released, which coincided with C# 5.0. And in that 10-year span of time, there were actually several options that were introduced of implementations of asynchronous programming. And I'm not going to take the time to talk about them because, frankly, it wouldn't add a whole lot of value. But if you're curious, I'd recommend reading this book. I'm going to point to it again at the end if we have time. Async in C# 5.0 by Alex Davies. I'm holding it here in my hand, published by O'Reilly. He does a really good job with introductory topics and spends several pages just walking through the process of manually implementing an asynchronous style of programming using some of these more historic approaches. But when C# 5.0 was released in 2012, again, that coincided with .NET Framework 4.5, which, as we talked about a little bit earlier, coincided with the Windows 8 Store API, so you could build fast and fluid applications for the Windows Store for the first time for both mobile and desktop. The async language feature was first introduced. So simply put, the C# async feature allows you to express what you want to do after a long-running operation is completed. It's easy to read, it's easy to implement, as actually it's easier in some ways to implement than a synchronous operation. But it looks a lot like a synchronous operation, any other method call that you would make in your code, but it behaves asynchronously. So C# async and the await operator and the task object, those three together enable an implementation of what's known as the promise model of concurrency. And it's known by several different names depending on which programming language you're looking at. In JavaScript, it's known as promises, and some cases even known as futures. Most programming languages simply refer to this as async or asynchronous software development. But the key idea, which honestly is a little bit mind-blowing for me, is how the resulting value from an asynchronous method is actually handled. The promise model breaks apart and makes a distinction between making a call into the async method and what you get back from it, the value of the result that we would expect to get back. And so maybe looking at a line of code might help in this particular case. Basically, it splits this into two parts. Good, I still have my mouse. All right, so first of all, it's going to call this getAsync method, and what is returned back from this async method is the promise of a future value. Now, at some point in the future, once the client's completed the getAsync operation, it will take that future value and it will actually assign it to the resulting value from this to this variable called message, and then it will continue on with the rest of the work. So once the .NET Framework runtime attempts to execute this right-hand side of the code, it knows it has a promised future value. It's like an IOU. We'll come back to that thought here in just a moment. This allows the thread of execution to put this method call, or the remainder of the method, the code that you don't see here that would come after this line of code, it will put that essentially on pause, and it will return control back to the caller of the method, which you don't see on this slide, but that's above it. So this could allow, for example, the UI thread to continue to receive input from the user so that any swiping operations or clicking operations will be accepted by the user interface, or in a server scenario, it would allow that to begin processing a different request on that same thread of execution. So once the right-hand side of this method call is complete, it will basically raise its hand. It'll flag down the .NET Framework runtime. It'll notify it that it's ready to resume. And the .NET Framework runtime can then pick back up where it left off from. It'll assign the result of the operation to the message variable in this case, and then it will continue on executing the remainder of the code below this line of code. It'll just pick it back up and continue on. So honestly, there's a lot more to it than that. That's a very simplified working model for the moment. But the key point to all of this is that the .NET Framework allows the current thread of execution to continue on, even though the original instruction has not finished yet. So we haven't finished this getAsync. We're still waiting on it to complete. But the .NET Framework runtime says that's okay. I'll put a peg in that right there. We'll come back to that later. I'm going to continue on, or allow the application to continue executing. So the .NET Framework is really left with an IOU, a promise that at some point in the future, it's going to have the result that it was hoping for. So this IOU, this promise, is returned from the async method in the form of a task object. Now, you don't see the word task represented anywhere, but this getAsync actually returns back a task to this value. And the task object keeps track of the progress and the future value, the result of the operation. It also contains some helper methods that perform async-related tasks, and we're going to look at some of those in just a few moments. So the key takeaway is that whenever you call an async method, you get back a task object, And in fact, in most cases, whenever you call an async method, you're going to get the generic version of a task, like task of t. In this particular example here, what gets returned back, and I only know this by looking at MSDN or actually IntelliSense, by hovering my mouse cursor over the word get async, it returns back a task of type HTTP response message. So I have a promise that in the future, I'm going to get an object called HTTP response message, which happens to be an object that gives me access to the resulting value that it pulled off of that website. And then we can use that object to go ahead and retrieve the raw string payload that was delivered back to the getAsync method. So as a result of working with a generic version of the task and the var keyword, which is another cool compiler trick that we don't really have time to talk about, implicit local variable declaration, we as software developers can actually remain blissfully unaware and unconcerned about all the complexity and all the machinations that the C# compiler and the .NET framework had to go through to get all this to work. So I'm going to try and boil this down for brevity's sake. After you build your application and you decide to create a release version of your code to be deployed to another computer, at that point, the C# compiler takes your C# code and it compiles it into something called IL, or intermediate language, and it packages it into a .NET assembly, either a .exe or a .dll. After you deploy it, a final compilation step called just-in-time compilation, or JIT, will take that intermediate language and compile it into a version of the assembly that's optimized for the host computer's hardware architecture and the operating system. Hopefully, at some point today or some point in your history, you know a little bit about what's going on with the compiler and how it creates a .NET assembly. So what I want to do, though, is talk about what happens and back up to that previous step. Whenever the C# compiler is actually parsing through your code and converting it into intermediate language, it encounters a call to an awaited asynchronous method. It'll actually splice up your single method into multiple methods that are essentially what I call magic callbacks. These will be called upon the completion of your asynchronous operation. And I use this term callbacks. That's something that's kind of special to software developers. It should ring a bell if you've written code in any other language, like JavaScript, for example. Callback method is a term in software development that means that the method is essentially registered for use upon the completion of some event. So in this case, the event is the completion of an asynchronous method call. So I call this a compiler trick. Admittedly, that might sound a little bit dismissive, but there's actually a massive amount of complexity behind it, which makes this an especially innovative feature, that they were able to do this with all the complexity and make it so simple to use. So the .NET Framework runtime manages the execution thread, telling it which magic callback method to perform next until it's finished all the pending async method calls. And to help illustrate this, there's actually a really helpful, let me bail out to Internet Explorer. I made a quick link here. Let's see, bitdo/async diagram, and this will pop open a specific portion of this article about async and await. And I'm not going to take the time to go through this right now. Hopefully you can see that on screen. But this is actually walks you through step by step of what's going on and how it's actually being performed under the hood from the .NET Framework's perspective, what the .NET compiler did to this code, and what that means basically. So basically, to recap, there's get back here to my slides, and I am way farther in time than I am in the course of my examples, so we'll get to those pretty quick. Sorry about that. Let's go here. So let's recap. I gave you the high-level background that's really necessary for us to move forward from this point. Hopefully that all made sense, because async, await, and task takes care of so much for you automatically. You should be able to use your working knowledge to really forge ahead now and understand the why. Why are we doing this, and what are we actually accomplishing? So there's really 3 takeaways. In fact, if we just ended the session right now without any code examples, it would be quite disappointing, but you get the basic gist of what you need to know. So first of all, there's 3 main takeaways. First of all, some types of code are just blocking by nature, and blocking is bad. It makes client applications unresponsive to the end user, and it ties up shared resources on a server application, and potentially the worst case scenario is that it'll become completely unresponsive to additional incoming requests. And then The second thing that you need to take away is that there are two fundamental kinds of blocking operations. There's CPU-bound blocking operations, which are calculation intensive. So the CPU is churning through a massive amount of work and it's busy the entire time. And there are I/O-bound blocking operations, which means that the CPU is just sitting around waiting for a response from a remote resource. Hopefully it'll get it someday, but it could be waiting in terms of seconds, not milliseconds or microseconds. And then the third point that you need to take away is that in C# 5.0, so that was what, 5 years ago, it introduced the async and await keyword, which together with the task or the generic task object, they provide an implementation of this promise model of concurrency. And so as your application is running it and encounters an async call to an awaitable task, it'll make a mental note to come back to that spot and continue executing, and then release the thread of execution to return to the caller. So once the async operation is complete, the .NET Framework runtime will return and continue where it left off. And behind the scenes, the C# compiler is rewriting your application to magically make all of this happen. All right, so finally it's time to actually write some code. Hopefully we can fit in a bunch here. And what I needed was a really interesting example, something that could potentially run for a long time, but I didn't want to use something just like task delay, which just makes the computer just sit and spin. I wanted to do something a little bit more realistic. So I decided to create an Azure function. And if you've watched the other sessions on .NET Conf, I have no doubt that there was a lot of buzz swirling around Azure Functions. It's one of Microsoft Azure's serverless computing services. And in my own work, and I've been using Azure Functions now for several months, I found them to be extremely valuable as part of a larger framework of technologies that allow me to build cloud-based applications. But in this example, I want to create a simple Azure function that does two things whenever you call it. First of all, it's going to wait for 5 seconds. In other words, it's just going to force that function to spin out in the Azure cloud for 5 seconds doing absolutely nothing. And my intent here is just so this will take a long time. And then finally, it'll return just a simple string. And on the client side, it's merely going to make a call to the Azure function itself. So we're going to write a WPF application, just real quick, drag and drop buttons, make click events, and ideally after we make a call out to the Azure function, and once it's complete, it'll update the user interface. But meanwhile, I'll still be able to perform other operations on the user interface. So let's get out here and let's jump to Visual Studio. Maybe we can at least get one example in, and then, I don't know, I've got so much material prepared, I could probably create a bunch of videos and we can add them at some later date to kind of demonstrate that. So one of the things that you're going to need, if you want to follow along, is Visual Studio 2017. I have the Community Edition installed. I have all the latest updates installed. You're also going to need to have the Azure Development Workload installed. So just so you know what I'm talking about here, let's go to Visual Studio Installer. And hopefully you see it pop up here in a second. And so this will give us the tools that we need to write Azure-based applications. So if we were to click, for example, modify, you need to make sure that this Azure development option is selected. If not, you want to check that and click modify and allow it to be installed. And then the final thing that you're going to need to do is that you'll probably see these notifications up here in the upper right-hand corner, and one of them will say something about an update to the Azure Functions tooling, and you'll want to install that. And so you'll have to shut down Visual Studio and start it back up again. But essentially what we want to do is create two solutions. So I'm going to close this one and reopen the first version of Visual Studio, and what I'll do is just create a new project, and I'll try to make this quick, but you should be able to follow along. I'll just call this function app1. We're not going to get cute right now, and we're going to run this function locally, but I have a deployed version up in the cloud just to make sure this actually does what we think it will do, and it certainly does. So once you've created the Azure Function app, you have to actually add a new Azure Function. So I'm going to right-click the project name, select Add New Item, and Azure Function should pop up to the top there. We're just going to leave the name function1.cs and click Add. This will allow us to determine which type of Azure Function trigger we want to use. In this case, I want to use an HTTP trigger, and we will set the access rights to anonymous. If you choose one of the others, you'd have to provide a key, and we don't want to do that just for this simple example. All right, so now you can see that we have our first Azure function. We can actually run this real quick just to show it. We're going to come back and we're going to add some code here to it in just a moment, though. All right, so we can see that our new function is at this endpoint. And I'll just copy and put it on my clipboard real quick. Shut this down. And what I want to do is actually comment out basically everything in here. I'm going to get rid of everything. I'm going to do it. Go down here and go task.delay, and then we'll set it to like 5,000 milliseconds, so that should be 5,000 seconds. And we're going to make this a wait, and we'll talk about what that does in just a little bit. And then here we're going to return from Azure functions. That should work, right? Oh, I'm sorry, no. Here, let's just grab this. And we'll put that there. And we'll just set name equal name. Okay, and that should suffice for now. All right, so let's go on and add then a second instance of Visual Studio. So I'm going to right-click in my taskbar and open up Visual Studio again. And I find it easier because once we run the Azure function, kind of want to leave it alone. This time I'm going to create a new project. We're going to select the classic Windows desktop, WPF app, and here I'm going to leave the name of the application alone. That's fine. We're just creating a quick demo. Javier, am I okay on time? Because we started a little bit on the late side, but do I need to wrap it up here? This is going to be wholly unfulfilling.
Hey, sorry, Bob, I was muted. Let's go for another 5 minutes, if that's cool.
Okay, I'll try to fit it in 5 minutes.
Awesome, that'd be great.
Thank you, sorry about that. So here I'm just dragging buttons from the toolbox into the designer surface. And let's go ahead and take our text box here, and we're going to drag this and put it here as well. All right, so we have two buttons. Let's create the first button's click event, and then I'm going to double click the second button to create a click event for that button as well. All right, so now we have the click event for the first button and the second button, and I was going to show you how to call it asynchronously, but that's really not pertinent. Let's, so that we can get some example working here, just let's actually create a simple method that we're going to call private, and I'll start off with task. Private async task, calling async. And then here I'm going to go var HTTP client equals new HTTP client. The pressure's on. And it won't find that, so I'm going to hit Control period on my keyboard to actually add the using statement for system.net.http. And so here we're going to go var message equals, and here's where we're going to use await HTTP client, and we're going to call the get async. Now, hopefully on my, no, I don't have it on there anymore. Let's run our other application one more time so that we can grab off the actual location, the endpoint for our Azure function that's running locally. And we will just leave that running while we switch over to our WPF application. And here I'm just going to paste in a hard-coded location to that function. And then var content equals await message dot content dot read as string async, and then return content. Awesome. And this should be task string, and that satisfies it. Okay, so what we'll do here is just create a little private void print, and then we'll just say whatever the value is that we want to print to screen. It'll just be easier this way. And so we can simply do something like the text box name. Let's give our text box a name. So my text box, and let's save that. And now we can reference that by its name. So my text box.text, and then we'll go plus equals, and then we'll take whatever the value is and go and add an environment dot new line. Yeah, that's good right there. So now what we can do is actually, when you click the first button, we'll just do print still responsive. And then when you call the second one, what we'll do is actually call into our calling async. So var result equals calling async. All right, and it's going to give me a, what we'll want to do is call this and await it. All right, and it says that we can't use the await because we have to make the method async, which we're doing now, and then I think we may have to even come back. This is not going to work because it tried to rename that method using that naming convention. But ultimately then what we want to do is print the result. All right, so let's see what we have so far, and hopefully we'll get at least a little way before we see what we need to do next. We have our Azure function running. Hopefully this will work, and it won't. Let's see what we got. Oh, yeah, so this is going to be void in this particular case because the method signature for a button click event is void, not a task. All right, that seems to work. So let's see if we're able to get still responsive. So let's click on our button, and I'm going to click still responsive. And then after hopefully 5 seconds, we got our hello back. So you can see that even though we were tied up with a call out to our Azure function that took 5 seconds, we were still able to create a responsive application. In fact, I can click this 3 times and still click buttons here. And I get the hello, hello, and hello. So I have a lot more. I may have to create some videos, just post them out on Channel 9. I apologize. I've got a little wordy there, but let's talk for one quick second, then I'll wrap this up, about what's really going on here with the await, the async, and the task. So let's get to that spot in my notes here. So this is async keyword. What is it really doing for us? It's actually doing 2 things. It is a message to the C# compiler that, first of all, this method can use the await operator here inside. And that await operator is used to designate the suspension points in the execution. And again, I would refer you back to that image that I pointed you to earlier, and we'll see that here on the slides at the very end. And then the second thing that this async keyword does is that the method itself can be awaited by methods that are calling it, like we did right here in this line of code. And so the await operator, again, is just telling the compiler that the async method can't continue past this point until the awaited asynchronous process is actually complete. So in the meantime, control returns to the caller of this event, which is this button click, which is the UI thread, and it allows us to continue to click the other button, still responsive, and then be able to post things to the text box. All right, and then finally this task object, what's going on there? Well, basically it's a state machine, and it represents this entire process of all the ongoing work. It encapsulates information about the state of the async process, and eventually either it delivers the final result back or it'll throw an exception if we can't, for example, find this endpoint and it doesn't do anything for us. So real quick, let me just shut down our Azure function, and then attempt to run our application one more time. And what we'll see is that our task will blow up whenever we click and we start trying to run, and oh, we hit a runtime error. So we can use the typical try catch around it. That will work, and we get the satisfaction of working with this code as if it were synchronous, but we get the value of returning control back to that UI thread. All right, so I think I've used even more than my 5 minutes, and maybe, Javier, someday I'll have to come back and record the rest of this. I apologize. I got a little wordy on that one.
Hey, no, Bob, you did great. Thank you so much. You know what? When it comes to this kind of content, you just have to have as much time as you need it, right? There's no way around it.
Right. I'm used to recording videos, and so there's no time limit. In fact, the more time you spend in a video, the better. It just makes it look like you have more content. So it's my experience showing through here with the live event.
And this is why we have you on .NET Conf, right? Because we want you to share this kind of knowledge to everybody who is watching right now or going to be watching, you know, and after we post a video up. So, all right. Well, I think this wraps it up. So, Bob, any last words?
No, hey, thanks for watching if you're still with us, if I didn't run you away. And I'll try to find a way, maybe Javier and I can work on this later and find a way to put the rest of the content out there. But thank you for your time.
Yep, sounds good. Well, everybody, we're watching .NET Conf. This is day 3, Beginner Day.